Okay. Okay, now for the second talk of this afternoon, we will listen to Julia Staffilani from MIT, who will talk about almost sure well-posedness for dispersive PDE. So please go ahead.
Thank you so much for the invitation. I think I'm probably the farthest away from this group, so thanks for giving me the opportunity to talk. And I was really happy to hear from Daniel and Jeremy and Lisa to mention at least dispersive equations, because that's going to be the topic of the talk. And I want to give more like a historical perspective, how ideas from probability and so on were introduced in the field that had been studied always in a deterministic way. So for that, I will start from 1990. That was around the time when I arrived at the University of Chicago, and Koenig, Pons, and Vega were implementing this new method to study the flow map. So, I mean, the existence, uniqueness, and stability of solution to certain dispersive equations. And some of them have been mentioned, the KDV, the NLS, the KP, and so on, at a very low regularity. The reason for that is because these systems represent apparently quite a lot of things, but in particular phenomenon in physics. And as such, they have conservation law. In fact, KDV and the 1D cubic NLS are actually integrable systems. But in any case, they have a conservation law which are related to the mass, that's mostly or the momentum, or the Hamiltonian, the energy. And these are written in general as L2 type spaces. So the L2, for example, represent the mass for the NLS equation. The H1 appears in the Hamiltonian as the kinetic energy. So you would like to stay within these spaces. And that had not been possible until this work in general of Koenig, Pons, and Vega, because the methods used until then were methods of energy methods. So they just require more regularity. I will mention a little bit more about that in a second. So what they were using were tools of oscillatory integrals, and which is part of harmonic analysis, and in particular Fourier restriction theorems. These methods are completely deterministic, and all the results here were deterministic in the sense, give me an initial data, I can tell you whether there is flow for all time or locally. So then around 1991, this is what Koenig told me, he's my advisor, was my advisor. He gave a talk at the IAS, and in the audience there was Spear from Leibowitz, Rose, and Spear. And he asked if it were possible to use these techniques in order to prove the existence of the flow for the equations, in particular NLS, in the periodic setting. So why was this question asked? The reason was that they had proved, and has been known for a while, that some of these equations had measures, such as the Gibbs measure, that were well defined. And one would like to prove that these measures are invariant with respect to the flow map. Of course, assuming that this flow existed. And I wanted to zoom in a little bit on these questions and try to figure out what were, at that time, we're talking about early 90s, the difficulties to put forward this program. So let me take as a particular example the NLS. So this is the usual, I is the complex number, the T Laplacian of U, and this is the linear part. And we have here the nonlinear part, which we usually write as this power, the absolute value of U to the 2K times UK, here just any number, natural number. And there is a lambda here, which tells you whether you are in the focusing or defocusing case. And we are giving an initial data, and we're going to look at this problem in the periodic case. As I mentioned, up until then, people knew how to do how to deal with the situation where X was in RD, meaning no boundary conditions. And I'm going to explain in a moment why periodic is a completely different kind of beast. So the Hamiltonian, which I mentioned, has the kinetic part in here and has the potential part here. And this lambda, whether it's positive or negative, is actually relevant, because if it's negative, there could be competition between these two pieces, the kinetic and the potential, making the Hamiltonian possibly negative. And there are blow-up results, so the flow might not be global, flow in time. One exponent that will tell us whether we are in a situation in which there is, the kinetic part is stronger than the potential and the same kind of order, or the potential stronger than the kinetic part, is given by the so-called critical exponent. So what does this measure? Well, if you take the HS norm in this exponent, so you take as an exponent of the Sobolev space, the homogeneous HS norm, then the HSC is going to be invariant for this equation. As you see, it depends on the dimension and it depends on the order and linearity. So whenever you have this problem here, you will have a critical exponent, and I would like to call this deterministic critical exponent because there's going to be a probabilistic critical exponent coming up in a second. So if you are in this kind of norm, you will be invariant. And if you are above this norm, then the kinetic part is stronger. If you are below, the potential part is stronger. Anyway, so this is all deterministic so far. Now, let me go back a little bit to the Gibbs measure in this particular situation of the NLS I'm looking at. Well, in order to define it, you have to normalize the nonlinearity. You guys are experts, so I don't need to explain this. This is via the weak order, and you're going to have, of course, correspondent Hamiltonian at this point, depending whether you normalize or you don't. But if you do, then you can, and I will tell you for which dimension, for which K, and so on, you can make sense to this very formal way of writing the Gibbs measure. So the question now becomes, can we define the Gibbs measure? So what are the dimensions? What is the nonlinearity for which this makes sense? And assuming that you can define that, can you prove that there is a flaw in the support of this measure? And whether with this flaw, once you prove that it exists, the measure just in the question 1 is invariant. Okay, so let me first talk about the measure and then talking about the flaw. So here, I'm not an expert on this at all, but by checking the literature, well, the question of proving the existence of this Gibbs measure is a non-trivial one. Is a major problem in quantum field theory, but at least what we know at the moment, according to what I have read, is that if you are in dimension 1 and 2, and this is for the Schrödinger problem that I just introduced, and any kind of nonlinearity, so lower dimension, any kind of nonlinearity, any power k, this is the measure makes sense. Glimm and Jaffe proved that. In dimension 3, if k equals 1, is also proved. This k equals 1 corresponded to the cubic, also been proved. We don't know for k greater or equal than 2. And for d equals 4, dimension 4, not possible to do that, to write the Gibbs measure. And if you are in the focusing case, or I'm missing a g here, then in dimension 1, you can define it for any k, but with some restriction on the size on the support. And if you are in dimension 2 and k greater or equal 1, not defined. Okay, so this is the panorama. I'm not going to talk at all about the Gibbs measure, in fact, but I just wanted to say that this is not always possible to define. And let's think about the support for a second, because this is relevant when we're going to look at the flaw. So the support of this Gibbs measure, whenever it's defined, is in the intersection of all, at least this is a good way to think about it for us that we do well-posedness of the dispersive equation, is the intersection of the Sobolev spaces HS for S strictly less than 1 minus d over 2. Now, I would like to remark that in dimension 1, if we want to show that there is a flaw in the support of this Gibbs measure to then prove that it's invariant, well, we will need to be able to say that there is a flaw in H 1/2 minus epsilon. And in dimension 2, we need to be able to say that there is a flaw in H minus epsilon. Now, when I say there is a flaw, well, at the first stage, people were thinking about a flaw in a deterministic sense. But I will tell you in a second that this has to be changed if you want to get some results. So let me, for you, maybe give a graph that it's quite telling. Well, in general, what you see is that until 1991, using this energy method, which has to do with a priori estimates, people knew that there was a flaw if you had a regularity or at least d over 2 plus epsilon. Basically, this is due to the fact that in order to run this argument of energy method, you need to know that an L infinity norm is bounded, and then you use the simple Sobol embedding. That means you have to be in d over 2 plus epsilon, meaning that you really like to be in a Sobol space, which is an algebra, so that you can control the nonlinearity, which is a product of function. So in this little line, here's where the space HD over 2 plus is, and we have the flow for anything which is bigger than that or smoother than that. On the other hand, in terms of the Gibbs measure, in the support of the Gibbs measure is in anything which is less regular than 1 minus d over 2. So we are in this direction. And hence, in general, there is really no intersection between these two domain or regimes, and hence the question was moot at that point in terms of the invariance. Okay, so let's go back, or let's start by talking with work of Bourgain in this kind of question. So when Koenig gave the talk at the IAS and Spear asked the question, Koenig said that he didn't know the answer in the periodic case for the following reason. So let me explain. So you would like to look at this initial value problem. We have normalized it with the weak order because we were thinking about the measure. And we know that we cannot solve this obviously in the classical sense because we don't have enough derivative. So by using the Duhamel principle, we're going to transform this question of the initial value problem into a question of integral equation. So this tells us if you can solve the initial value problem, you can solve this integral equation. Going back, of course, you have to be careful because as you can see here in the integral equation setting, you need less regularity. That's exactly the point. So what is this STU0? This is nothing else than the linear solution of the problem, meaning you set the nonlinearity equals 0, you solve. And then this is the integral 0 to t, and then it's the same Schrodinger group applied now to the nonlinearity. Obviously, this is not explicit because I'm telling you in terms of u itself, so it's not really a form that we can use explicitly, but it's going to be relevant for us. Now, one thing that we want to check is first, what is the formula for the linear equation? And actually, that's explicit, and you can do that via the Fourier transform, which in the periodic case you can do easily. And in fact, by using the Fourier coefficient of your initial data, you can write the whole solution as a sum in k, and then this oscillation e to the I t k squared that comes from the fact you're solving the Schrodinger, and then xk. If you're solving, for example, KdV, you will see here k cubed. Okay, so now why the arguments that Koenig, Pons, and Vega were developing didn't work here? The reason why it didn't work is because if you look at this expression, but when you are in RD, instead of the sum here, you will have an integral. So you will have an oscillatory integral, and there are lots of techniques which are basically based on integration by parts that you can control, you can use, and say quite a lot of things about this expression if you have an integral. But if you are in the periodic case, you have a sum, you cannot integrate by parts, and hence none of the arguments that Koenig, Pons, and Vega had could be used here. Okay, now in order to go back at this integral equation, look for a solution, what you would like to say is that the integral in time is a perturbation of the linear part. So if you think about the right-hand side as an operator, then if you could prove that that operator has a fixed point, then you got your solution. So, but the question is, where can you do the fixed point? Well, that depends on how good of multilinear estimates you can prove for the linear part. And these multilinear estimates nowadays go under the name of Strickard's estimates. And that's what Bourgain was able to do. And this, again, it's all deterministic so far by using analytic number theory. And now it's, more developed, but in any case. So he was able to do this Strickard's estimate, and he was able to prove the following. So if dimension is 1 and we are k equals 2, that's the quintic NLS. Remember, the nonlinearity is absolute value of u 2 to the k times u, so that's the quintic. And the critical exponent is 0 in this case. he was able to prove just above this critical exponent, so we are in the subcritical situation, that you have a flow, local in time. On the other hand, if you remember where the support of the measure was, in this dimension, dimension 1, for this nonlinearity, well, we need to be below 1/2. So you see there is an intersection. So at least in this particular case, which is dimension 1, a cubic nonlinearity, the flow existed in a deterministic manner locally in time, but then Bourgain used the invariance of the Gibbs measure to extend from local in time to global in time. And he proved what Steele was asking for dimension 1 quintic NLS. Okay, so that was the first attempt to give a good answer, and the flow was done deterministically. But then, of course, you want to go to dimension 2 and the cubic NLS. That's the most physical one that people look at. Again, the critical exponent here is 0. And the Strickard's estimates and the local well-posedness in a deterministic manner was proved to be, and this was actually not trivial at all, locally in H epsilon. So that means if you are smoother than epsilon, you have your flow. It's a local flow in general. Unless you get to H1, you can use the Hamiltonian anyway, so you have that. But on the other hand, the support of the measure is for less regular than minus epsilon. So minus epsilon is actually a supercritical exponent. So there is no intersection here, meaning that the flow that we knew, even from this more sophisticated techniques of Bourgain, was not reaching in a deterministic manner the support of the measure. So something else had to be done. And here's where the interesting thing happened, and Bourgain's idea was the following. Now, the typical element on this support of the measure for this dimension, for this nonlinearity, is this, where G and omega for us are independent random variables, if you want. Okay. Now, we know that we cannot evolve this initial data in a deterministic manner because we are below whatever the Strickard's estimate allows us to use. So what it was doing was the following. Instead of solving for this initial data, it's looking at a different kind of flow. It's going to take the original flow minus the linear evolution of the initial data. In other words, maybe it was solving for W, where W is the solution of your initial problem minus the evolution of the linear evolution of your random initial data. So in other words, what it was looking at is this equation here. Now, this is an equation of W. And sorry, it's important to remind you that we are looking at the weak order nonlinearity, of course. And it turns out that solving this problem is better in the sense that the W acquires a certain regularity. And in fact, the reason being that in the nonlinearity, you have products of this random linear evolution, and the independence of the Gn helps you in controlling this nonlinearity instead of just having the one for W. So what it was able to prove was that actually this equation here, it's better behaved, it's smoother, and it lives in H epsilon, where now we have the Strickard's estimate. Now, this should remind you, since you guys are all experts in stochastic PDE, that it's something that maybe Prada de Bush, I'm sure other people have employed quite a lot for stochastic PDE when you have noise. So you look at a part which is a linear evolution with noise, which has more structure, and a part which doesn't have much structure, but it's smoother. So that's the trick. Now, Bourgain result, as I mentioned, first you solve W, then you have, and this is local in time, then you have a flow, phi t, you reconstruct by adding the linear evolution, then you use the invariance of the measure to go from local to global, and you answer the question. Now, this was like mid-90s, so there was quite a lot of time in between then and now. And I want to mention just a few things. So after Bourgain, there was some work of Tadahiro O for KDV type systems. and still dispersive equations. And then Burke and Setkov looked at a semi-linear wave equation on compact manifold dimension 3. And I have to say that this is much, in a way, is a weaker result of the techniques are weaker for this result of Burke and Setkov, because the wave equation actually has a smoothing effect. So they didn't have to do the complicated analysis that Bourgain did. So it was a more straightforward in a sense. And then there are many other results that I'm not going to mention here. In fact, maybe I should check my time. Yes. That came about. One thing that I really want to mention is the following, that once it was figured out in our group of people working in the dispersive equation that randomizing the initial data was actually improving the regularity of the problem in a certain sense, then people start using this idea also in RD. So not just in a periodic or compact manifolds, but on the whole RD. So this might sound a little bit weird, because how do you randomize in that kind of setting? So maybe this is something new, and I just want to mention. So if you are in RD, how do you randomize it? Well, I'm looking at my initial data, U0x. So whenever you're looking at an initial value problem, you have your initial data. Now this is defined in RD. And what we look at is first on the frequency space. Of course, there's a Fourier transform. We look at frequency space, and that's RD again. We're gonna decompose it into cubes that are just of size 1. They are unit cubes. So this is different than doing at the dyadic decomposition, because the cubes are all of the same size and they are centered in the lattice ZD. Then you take a partition of unit in this world of the Fourier world in a way, and you look at projections on these cubes. And what you consider to be the randomization of your original initial data is going to be U0 omega, which is the sum K in ZD. This is the lattice of GK omega. This is, again, the independent random variables. And then the projection operator on U0x. So it's kind of like taking in the frequency space, you divide into cubes, and then the pieces of your functions that live in those cubes are going to be randomly summed using GK. And it turned out that, for example, in the work of Lerman, Mandelson, and Benio and Popovniku, in this, doing this, you could prove, in fact, existence of solution of supercritical regimes, and compare that with the type of blow-up results that are proved in the supercritical regime as well. So this has been an interesting line of work as well, and I wanted to mention because it's a little bit different than what people see. Now, I wanted to talk in particular, and not at all in details, because this is a very complex type of work, on a major improvement on Bourgain's approach. So Bourgain, if we look back at when the measure is defined and what Bourgain considered, so Bourgain left open the problem for dimension 2 and any nonlinearity k greater than 2. He only considered the k equals 1, which was the cubic. And now we can consider all the, in principle, the measure is there. We should check whether the flow can be defined in the support of the measure. And this was recently solved by Deng, Namod, and Wei in a really extraordinary tour de force by introducing what they call random averaging operators and random tensors. So I'm going to give a very, very brief idea of this. As I mentioned, the work of Bourgain is sort of the version of the Prado-Debuche techniques, but in the dispersive world. But we know that in the stochastic PDE world, things had evolved quite a bit. And in particular, let me just slide here. I wanted to mention the two approaches, one by the regularity structure and Martin Hare, and the other one is the paracontrol calculus of Gubinelli in Keller-Pertoschi. So the Martin Hare's approach I'm simplifying here a lot, but the punchline that I wanted to mention is that his tools works very well if you consider or you look at solutions that and you measure the regularity with a Holder regularity, which is really appropriate for any kind of elliptic parabolic type of equation, no matter how singular they might be. So it's not obvious how to extend this approach to the dispersive world, where instead we prefer Sobolev spaces of L2 type, because this conservation of energy and Hamiltonian that are basically based on L2. On the other hand, the paracontrol calculus, so Gubinelli and Keller-Pertosky, is much more suitable for the type of multilinear estimates that we already knew how to do via the Fourier analysis, Fourier harmonic analysis. So the second approach is what they looked at more closely. And if we go back to the work of Bourgain, we see that what he did was separating U, which is the solution, into the linear part, which is not, the regularity is whatever it is. The Schrödinger operator does not improve regularity, but it has quite a lot of structure because we can track exactly the randomness that is there. And W, it's smoother, although not that, there is no structure in there. So what Deng, Namod, and White did was to go back and look at W and in it figure out what is the worst part, the less regular part, and extract that and then recenter somehow. So what they look at was again, the linear evolution. I should have put here omega because this is random, but you know what I mean. And then this X, which is the least regular part of W, and this together has more structure, and W tilde has more regularity than the original W itself. So more specifically, what they did was to define actually what this X in the previous slide was. And this was the sum in L much smaller than N. So there are, like I said, this is the world of Fourier analysis and harmonic analysis. So we split everything in different frequency size. So what I'm indicating here with L and M are the size of the various frequency. So when I sum in L, I'm not going to get all the way to the frequency N, but I'm going to stop much before. And then this PLN are random averaging operators. Well, you have to go and look at the structure itself, but it's important to remark for what I'm going to talk about here, that the coefficients of this, so there are certain coefficients here that we sum for this operator, and they depend on the G and omega, so the random variables. And since I'm summing way before capital N, they are all independent of the big frequency N because I sum just up to them. These are dyadic blocks, so they do not intersect with each other. And then there is the smoother part. Now, this idea of separating into frequencies that are lower and higher so you maintain a structure of independence actually already appeared as a germ, in a sense, in a thesis of this brilliant guy. He is a student of Terry Tao, just graduating, and he was really the one that introduced this kind of idea of splitting into low and high frequency and not having intersected. So let me finish here. I think this is my last slides. After they resolved the question of invariance of the measure in dimension 2 for any kind of nonlinearity, they discovered that actually whenever you consider this almost sure flows instead of the deterministic flows, what you should be worrying about is not really the critical exponent that I computed before, which is our deterministic critical exponent, but you should be worried about a probabilistic critical exponent that they define to be SPR. Now, they describe very well in the paper where this comes from. I'm not going to go through that, But in the case that I'm looking at for the Schrödinger equation, of course, this will change depending which equation you look at. But for the Schrödinger equation with nonlinearity 2k plus 1, this critical exponent, probabilistic critical exponent, happened to be minus 1 over 2k, and it's definitely smaller than the usual deterministic critical exponent. And so their conjecture in their first paper was to show that you should be able to prove that there is an almost sure flow, so this probabilistic flow, above this critical exponent. And that's exactly what they proved. This flow, it's local. To make it global, since we are below, there are no Gibbs measure many times anyway, one needs to do something else, but at least locally this flow exists. And in order to prove this, the existence of this flow, they had to refine this idea of the introduction of this random operator P and L, and in fact they introduced random tensors. So this is more complex, and they in fact proved almost sure local well-posedness for any initial data U0 omega, which regularity in the Sobolev space can be measured with S, and that S is above this critical exponent. So I'm going to stop here, and I'm going to let Chenji Fan to take this idea a little bit further, and also to explain some results that are actually for the Schrödinger equation with noise. So I'm going to let him do that, if that's okay.
Okay, thank you very much for your talk. So Chenji, can you wait? I think someone needs to make you. Oh, no, please fine. Okay, so now we listen to the discussion by Chenji Fan.
Oh, I think I'm unmute. Okay. So hello, hi, how are you? So thanks for giving me the opportunity. And yes, I want to do a summary of Giuliola's talk and about what I have learned from Giuliola and from other people in the field. Okay, so I think most of the time I'm working on, and I think a lot of people in the PDE field are working on nonlinear PDE. Basically, is a linear part, and there's a nonlinearity. So people always start with the so-called local theory. And at the beginning, the local theory is always about the size of the data. Okay, so what do we mean by size of the data? You want to find some space to do conjunction, which means you want to find the right C alpha norm, the right LTPL XQ norm, or some right Sobolev space.
Chenji, are you moving the slides, or you're not?
No, I'm not moving the slides.
Okay,
yet.
good.
I will move the slides later. Yes.
Okay.
Yes. Yes. So at the beginning, it's all about size. But how do you decide the size, or how do you decide the space? Basically, you look at the linear PDE and you try to understand the linear flow, and you decide those space and you decide the size. So I think that's the beginning of how I learn about those PDEs. And later, I think the theory goes to the next stage. I think just as in Giuliola's talk, now your PDE still is a linear part and you have a nonlinear part, but you view the solution as a linear part plus a better part, which means do some smoothing estimates. I think this is a very good improvement in the local theory. Those sounds very simple, but it's very important, which means you begin to care about the structure of the solution, not only about the size. You want to say that the solution locally not only has the right size as the linear solution, but actually looks like a linear solution. I think that's stage 2. And finally, I think, in stage 2, it's really not too special about random data or stochastic PDE. Basically, all PDE has this feature. But I think something is very important in random data or stochastic PDE is really your initial data also has a structure, right? Previously, when we talk about structure, we're talking about the structure is the solution locally looks like a linear solution. But now your initial data also has some structure. I think that's how the field is now. So I think now the field is people are interested in nonlinear PDE with some very structured data. For example, if you consider random data, your initial data looks like a summation of Gaussians. If you look at stochastic PDE, the noise in some sense is like Gaussians. Of course, people has really worked on this idea and go very far. People can work on more complicated nonlinear answers, and people can do perturbation around complicated objects, and people also do higher order expansions. So somehow I want to talk about some models I studied, and hopefully we can see some features in those models. Okay, now I'm moving the slides. So first I want to talk about a so-called 3D mass critical defocusing NRS with a conservative multiplicative noise. So if you look at the equation, basically it is a very classical 3D mass critical defocusing NRS. If you forget about the V, if you take V equal to 0, this is a very classical equation. And in 2012, Dawson proves, oh, sorry, I want to apologize first. So because this is like very informal discussion, so I'm missing a lot of citations, but I will mention the important work, directly related important work. So if you take those V equal to 0 and you consider LX2 initial data, basically this equation was completely studied in the work of Dodson. He proves that all LX2 initial data would generate a global flow, and in long time, the flow would look like a linear solution. Okay, so what I want to talk here is I want to add some noise here. And here, if you look at this model, so first it is added with a conservative multiplicative noise, which means if you look at the solution of this equation, at least formally, the LX2 norm of the initial data will be conserved in a pathwise way. And you will also see there's a T to the negative gamma, which is really imposed time decay. So of course, I will only consider gamma larger than 0 or gamma equal to 0. I have to admit this T to the negative gamma is an imposed time decay, but hopefully I can convince you somehow it's still of interest to study this model. We will only consider Swartz V here, so there's no need to worry about the rough V. So it's not a talk about singular SPDE. It's very nice noise. So initial data would be posed in the so-called LX2 space, but the long-term result I will talk about would be non-trivial even for Swartz initial data. So what do we want to model? Of course, I want to model a simple equation, which is equation 2. Basically is mass critical NRS with the multiplicative noise, and the noise is colored in space and white in time. So I think such model was first studied, maybe not in this particular model, but such types of models were first studied by the Boyd and the Bush. Okay. So first, let me talk about some local theory and global existence. So if you want to only study the global existence, which means you want to exclude the finite time blow up, but within finite time, the decay doesn't matter. So let's just take gamma equal to 0. So there's 3 possible formulations of local theory. There may be more, but I think there's 3 possible formulations. So the first one is you can find some stopping time tau epsilon, such that the system is well posed within 0 to tau epsilon. Of course, you need to prove that tau epsilon is larger than 0, almost surely. And you can also talking about there's some epsilon, which depends on your initial data U0, so that your system is locally well posed within 0 epsilon. Of course, you can talk about the system is locally well posed within 0, 1. And of course, if we can prove the third types of local theory, this would directly imply global existence, since you have mass conservation law in a pathwise way. So this is the first result I want to talk about. So I think this is around 2017 or 2018 maybe. But basically for every U0 in L omega LX2, we can find a flow which is locally well posed within 0, 1. Let's not worry too much about this LT alpha LX beta. This is just some standard Strasser's norm. The point is we can find the flow is locally well posed within 0, 1. And we can have very good estimates for this space-time norm LT alpha LX beta in the L omega rho sense, which means if you do an expectation, you have a good estimate from PDE viewpoint. Let me remark here, the initial data is very important for us. The initial data should lie in L omega infinity, LX2. And then you can prove this estimate for all rho from 1, but strictly smaller than infinity, okay? But by no means that if you only care about the estimate of type 4 for some certain rho 1, you can assume U0 is in some L omega rho 2. This is not okay. If you assume U0 is in L omega infinity LX2, you can have an estimate for all L omega rho. But if you only assume your U0 is in L omega rho for some rho, you can get nothing. At least if you use our methods, you can get nothing. So this result has natural extension to focusing case. Yes. So I want to talk very roughly about how this proof is done, and hopefully we can see some vibrato distribution method in this proof. Okay, so the proof basically has two parts. One part we call is called martingale control. One part we call modified stability. So first we want to consider the quantity phi. So let me remark, this quantity is really some stochastic convolution, and you want to have some maximal type estimates. Of course, if you use the martingale structure, you can have the maximal type estimates. So the point is, you first try to study this m star t, and you want to get some global LT alpha estimate for this m star t. And then you want to have a modified stability to perturb the equation when this m star t LT alpha AB is small. So how this is related to the so-called vibrato distribution method? So the idea is the following. So the point is, rather than look at the equation itself, you need to look at the equation or talk about stability from the viewpoint of the Duhamel formula. So you're just writing down the Duhamel formula, which is formula 6, okay? So the vibrato distribution method basically is, if you have a stochastic PDE with additive noise, you first try to solve the linear PDE with an additive noise, and then try to solve the rest part of the PDE as a PDE which is more or less deterministic, but with random coefficients. At least that's how I understand their method. So here the idea is similar, but first you have to study. First, the model here is a PDE with a multiplicative noise. Second, you cannot directly start with a linear PDE. You have to first find some this m star t and find the right interval AB so that this m star t LT alpha AB is small. Because if you're writing down this Duhamel formula, so there'll be an A here. So it's not that you have a decomposition independent of your Duhamel formula. You have to first find the right interval AB. Then you're writing down the Duhamel formula. Then you find this eta 1 and you try to solve U subtract eta 1. So I think this is somehow in same principle of those developments in this random data or in this stochastic PDE. Basically I feel it's very hard to go beyond the perturbations, but you can do slightly more complicated perturbations and to do perturbation around the so-called right objects. Here, there's two parts to make these objects right. First part, we need to find the right AB. Second, we are really doing perturbation around the mass critical NS. And of course, Dawson results for mass critical NS will be crucial to prove the results of Fan and Shi, okay? Okay, so how about long time behaviors? Let's go back to this model. But unfortunately for long time behaviors, I have to impose a time decay T to a negative gamma. But I think what's most interesting is what's going on when gamma equal to 0. Though this noise looks very simple, but this model is not that easy to handle. Indeed, if you consider the case gamma equal to 0, even for Swartz initial data, I believe nothing is known except for global existence. So global existence is kind of easy, but what's going on in long time, I think it's very unclear. Even linear is unclear. So even if you study this model, which means you forget about this nonlinearity, you only study this linear model. If you take gamma equal to 0, basically I think nothing really known except for global existence. But for small noise, I can obtain some decay estimates, which means you can post this guy to be 1, which means gamma equal to 0, but you have to post that V is small. Then you can potentially get some long time decay estimate for the linear solution for the stochastic PDE. And in short, in long time, the linear solution would look like the linear solution to a deterministic Schrodinger equation with random initial data. But I basically so far don't know how to recover Dawson result, which means how to study the long scattering behavior. But of course, if the time decay you impose is too strong, then the problem is not hard. For example, if gamma is larger than 1, the problem is essentially trivial because T to the, this is not integrable, but if you consider T to negative gamma, gamma larger than 1, this is of course integrable. And because this is integrable, you can use some Minkowski argument to reduce, or triangle inequality argument to reduce to a local theory. But you can do better. Because from the viewpoint of Berkholder inequality, you should study LT2 integrability rather than LT1. So the natural step to do is actually the case gamma is larger than 1/2. This viewpoint is actually well illustrated by a very interesting work by Her, Rockner, and Zhang. And they do obtain the scattering asymptotic when gamma is larger than 1/2. And more precisely, they handle noise with finite quadratic variation in time. So I think the next natural step is to consider the case gamma equals to 1/2. Now the noise will be of infinite quadratic variation. And from my perspective, this means you really have to inject a lot of randomness into or stochastic noise into the system. And if you can still say the scattering asymptotic, this really means you can have obtained some decaying behavior for the stochastic PDE. So I thought this was very hard when I was working with Weijing in 2018, and we want to working out gamma equals to 1/2, but this looks very hard to me. But actually, joined with Zihua Zhao in 2020, we actually recovered all the gamma larger than 0 case for the LX2 initial data. So let's don't worry too much about this LT alpha LX beta case. But basically, if you impose a slight time decay, you consider every U0 in L omega LX2, recall the result of me with Weijing already tells you can have a global flow. But the point is here, you not only have a global flow, you actually have a space-time global bound L omega alpha LT alpha LX beta. Recall if you have a global space-time bound, this means you have some decay, okay? And almost surely, we can prove this U will scatter to linear solutions to the so-called free Schrödinger equations. As far as I'm concerned, even for the case gamma equals to 1/2 and the Schwarz initial data, such result is new. But unlike the and I want to mention, unlike the deterministic case, the scattering behavior does not follow directly from space-time global bound, and extra efforts are needed to work out the asymptotics, okay? So if you have space-time global bound, from my perspective, you do have some progress, because this means if something is integrable, this means asymptotically it goes to 0. But we actually want not only asymptotic goes to 0, we want to know it asymptotic goes to 0 like a linear solution. This result also has natural extension to focusing case. And we do expect our results can be extended to the dimension d larger than 2. But the case d equals to 1 is conceptually harder, and I believe it needs new ingredients. So the proof actually refined analysis in previous joint work was shown in several different ways. And actually, when I work with Zihua, I realized if we use analysis with me and Weijing, we can actually handle the case gamma equals to 1/2. Because in our scheme, we already kind of use dispersive estimates. So some decay is indeed applied. But my previous work with Weijing cannot really handle gamma very close to 0. We can probably handle gamma is larger than 3/7, something like this. And I want to mention Dawson's LX2 result is crucial here and cannot be bypassed by simply consider some nicer initial data. Let me remark, if you consider deterministic LX2 mass critical NLS, if you impose extra regularity of the initial data, the proof can be simplified. But here in this model, even if you consider the Schwarz initial data, I don't know how to bypass Dawson's LX2 results, okay? So from this perspective, our results has a weakness, okay? From one perspective, this means the model is harder, but from other perspective, our result has a weakness because we are missing certain persistence of regularity. So we don't really know how to enhance our results for nicer initial data. We do can have some partial enhancements, okay? So I think the key observation here is, so let's forget all about those technical details, but I want to draw some similarity to Giuliola's talk. So the key observation is you have to find the right objects to perturb. Just look at those two equations. So I think usually people would view this equation, as a nonlinear dispersive PDE with a noise. But this turns out is not the right perspective, because if you use this perspective, you are basically consider this term in a purely perturbative way, but this term what gives you a big trouble. The idea really you should view this equation as a damped NLS perturbed with a noise. Of course, this noise would be worse than this blue noise, but you want to take this part into an equation. And you observe this is negative sign. This negative sign is a damping term, which means you have to use the structure of this equation and use structure of this equation, and this sign is in the right sign. Okay, so if this is plus, basically I have no idea how to do it. But this negative sign is natural because whenever you consider Strong-Tonowich correction, this will give you a negative sign. And yes, I don't want to talk about the technical details. I want to talk about one more example. So one more example I want to talk about is the 2D mass critical NLS, but this time with focusing nonlinearity, which means you have a minus sign here. So in a recent work joined with Donna Mendelssohn, we actually construct some log-log blob solutions with LX2 regularity with probabilistic methods, or in other words, random data theory. So the thing I want to highlight here is this equation is well posed in LX2 regularity, okay? So typically random data theory was applied in most of the time I say it will overcome the ill-posedness caused by low regularity data. So the typical result always looks like this. So there's some ill-posed result for some HS data when S is small. And you consider a randomized version of HS, and you have to say it's not ill-posed anymore. It's not well-posed. But here, in the LX2 regularity, this equation is actually well-posed. It's not ill-posed in any way. So here we apply the random data theory, not to overcome the ill-posedness caused by low regularity data, but to overcome some potential nonlinear stability. So I will not talk about any details, but I want to say the solution would be looks like U equals to A plus epsilon plus F. Here, A is not a rough, which means if you look of the regularity, I mean the qualitative regularity, A is very nice. A may be smooth to infinity, but A is very nonlinear and would blows up, which means the size will be very large and essentially goes to infinity. But this A would be of very detailed structure, which is a so-called log-log dynamic structure. So which means A is very large, very nonlinear, but we understand A. Of course, this is because after the first construction of log-log blob solution by Galina Pellerman, Merlin and Raphael has done really a systematic series of work to study this log-log blob solution in a very careful way. And of course, that's the work of Raphael and Coriander in the HS log-log blob solutions, okay? So we basically push this S to LX2. So this A is not rough, very smooth, but very nonlinear and blows up. So this F, but this F here would be random. It will be of low regularity. Low regularity means this is in LX2 regularity. And let me remark the stability of log blow up at LX2 is an open problem. And I think people is also debating about is stable or not stable. And I will vote no. Okay, I will vote it's not stable. So here your F is random, it's low regularity, and it's of structure, which means it's like a Gaussian and it's like a linear Schrodinger solutions. And here your epsilon, which means it's better than A and F in both sense. So epsilon is of smaller size compared to A, but you don't have too much structure of epsilon. So epsilon now is small in some sense, but missing structure. Epsilon is also of higher regularity compared to F. So which means epsilon is smoother than F, but also epsilon is not of structure. Epsilon is missing structure. So I think these answers will be interesting. It's like a rough, or not, I'm sorry, it's like smooth, large, plus random, low regularity, linear, plus small size and higher regularity. So I think that's where I want to stop. And thank you.
Thank you very much for this discussion, for this talk. So are there any questions from the audience for either Giliola or Chenjie? Okay, I don't see any questions so far. So maybe I can ask you a question about this last result that you were just presenting about the blow up.
Yes.
So does this mean that in the end you prove that you can find, so how do I see this? So you prove that you have a blow up, and can you prove that like almost surely for
That's very
close
good
enough
question.
initial data, you also blow up?
Very good. That's very good question. And the short answer is no. We want to say if we can prove that. So the point of this work is to give the at least existence of log-log blob solutions with LX2 regularity. And if you apply those Gaussian type estimate, of course, if you can show existence, you can show a lot, right? So you can somehow guess that it's of larger probability. So the exceptional sets would be of exponentially small tail. So it's like a very, very small exceptional set. But we cannot prove almost sure. I think a more interesting question in this direction is the following. So you can also consider mass critical NLS perturbed with a conservative multiplicative noise. So actually joined with Zhendang and Yiming, we construct some log-log blob solutions to that model, not of low regularity, but it's a NLS with a multiplicative noise. So it's like stochastic PDE. So I believe it's reasonable to conjecture in that case, you will kind of have, in some sense, almost surely or pathwise log-log blow up, but also we didn't get that. So yes, but for this case, so I think, yes, the short answer is no, but it is a very interesting question. And I believe it's very hard. So let me remark one thing to do if you want to prove something, okay? So there's only two known blow up around the ground state for this equation. So one is called conformal. I'm sorry, it's more than two, but essentially there's two. One is called conformal blow up. One is called log-log. Log-log is believed to be very stable, and conformal is known to be very unstable. But if you want to prove those almost surely log-log blow up, you want to exclude the possibility there's another possible stable blow up mechanism in this regime, but this is unclear. I'm not sure I answered the question or not.
Yes, thank you very much.
Yeah.
Okay, maybe a more basic question before we pass to the next talk. So from the talk of Giuliola, I understand that basically usually you have like a probabilistic local well-posedness, and then if you have an invariant measure, you can use that to get global in time. So are there any situations where even though you don't really have an invariant measure, you can still use some other way to get global in time, to go from local in time to global in time?
Yeah, actually, the answer is yes. For example, in the wave equation, that was done by work of Setkov and Burke, I think maybe somebody else too, in the sense that they were able to prove that the energy was probabilistically bounded. So like if you do in the regime of regularity of the initial data that you're looking at, if you try to prove the boundedness of the energy with those data, like for example, if you are looking, the energy is basically H1, but if you look at regularity below H1, of course, the energy is infinity deterministically, but probabilistically they prove that it's bounded, and hence by using that, they are able to extend. But for the Schrödinger equation, that's not the case, so has not been proved. On the other hand, there are now proofs of quasi-invariance for a certain type of energies, which are not the usual ones, for certain equations that are variation of the NLS. So in that case, then you can use that kind of quasi-invariance thing. But yeah, but that's basically, this is basically where we are at the moment. Yeah.
Okay, thank you very much. So there's so Andre has a question.
Hi, maybe just one small question, as I think there are no others. Simple one, basically, You mentioned random data theory and extension to probabilistic data. Could you maybe extend on the probabilistic implications of this work? I was thinking about random matrix theory and other possibilities. Thanks.
I cannot comment on that because I didn't. That would be great, and I would love to be able to say something about it, but I'm not. Yeah, so that's basically all. One thing that maybe I want to mention, which is not related to random matrices at all, but maybe that's a place where I might see something that's closer. So there is this big effort nowadays, which I didn't talk about it, but really has been done in the last few years about proving the existence of the kinetic equation coming from different models, whether it's the Schrödinger or some kind of variation of KDV or multidimensional KDV. And of course, there you have to use some kind of random data. You have to use some probability in there. So, and this is done by this group of Courant, Chattani, Germain, and then there is also Collot and so on. And then FAU, and then there is the group more in Germany, Ospon and Lucarin and so on. So that, in particular, the group in Germany, and I have done some work on this recently with my collaborator, Binh Tran, they use Feynman graphs and things like that. So I'm wondering if there is something there that's closer to than what we have been doing here. But I don't know. Yeah, the short answer from me is I don't know, because I don't know the field. So if somebody can see a connection, I will be really happy to talk about it.
Yes, I can see a short remark. So
yes, go ahead.
I don't know how to apply those random data theory to random matrix. But if you look at the work of Yuden, Dinamo, and Haitian, which is mentioned in Julia's talk, there's a word called random averaging operators. What's random averaging operators? Basically, you plug in a finite dimensional vector. If you do Fourier truncation, all functions are finite dimensional vectors. You have an output, which is also a finite dimensional vector. So which you do say a random matrix. And I believe in their random tensor work, they prove some interesting inequality, which would be of some interest to random matrix theory. So I cannot say the application. I just want to say if you use this random data theory, you will see random matrix, but maybe not the field of random matrix. You will see a matrix which is random. So, okay.
Yeah. Thank you.
Okay.
Okay, thank you for the answers. And okay, thanks again, Julia and Shinji, for the nice talks. And